Hi. Hi, everyone. We're excited to be here with you today, and we are going to be walking you through ZS KEPLER, our knowledge engineering platform for linking entities and relationships. Okay, so just some quick background on ourselves. I'm Ashley Poort. I am an engineering specialist with ZS Associates in our Architecture and Engineering Expertise Center. My background is in information science, but I've been a practicing ontologist and knowledge engineer for the past 6 years. Jaipal?
Hey everyone, I'm Jaipal. I'm part of ZS's technology practice and been operating in the semantic space for the last few years now, and helped a lot of clients build out our semantic products as well as data fabrics. I'm really passionate about this technology, and I guess everybody who's made it here is, and that's what we'll talk about today on how we can take unstructured data to the next level through knowledge graphs. All right, so there are many problems people brought up. I think the presentation before this, we also talked about the fact that there are many genes and diseases. It's still hard to figure out who has done what research. There's like hundreds of information or millions of information that's hidden in research papers that needs to be unlocked. Why is it hard to unlock that kind of information? So this question started coming up to us from multiple clients, right? Which talked about, look, this is a problem area we're looking into. People from manufacturing reached out talking about that predictive maintenance is a huge problem. Whenever any machine goes down or whenever a bioreactor is about to give out, we need to comb through hundreds and thousands of manuals to look for solutions, to figure out where parts are coming from, who made them, how do you fix them. And the more people spoke to us, the more we saw that they were thinking in terms of causal relationships and graphs, which helped us think about our solution right in this particular space. And going through these documentation, be it research papers or even be it manuals, we figured we are trying to get machines to derive insights from documents that were written by humans for humans, right? So even though humans are creating these documents, we write them as a person, and then we're trying to get machines to interpret them and understand them. So we said, okay, how do you solve this problem, right? How do you provide structure? So we don't need to sell the concept of a knowledge graph to this group, but we said a knowledge graph will provide you structure and AI will provide us scale. There are thousands of tools that are getting developed. In GPT was mentioned. There's BioBert, right? So our thinking behind creating a structured solution in the knowledge graph or knowledge engineering space was go off and chase a paradigm that people already know and people are already familiar with, but it gives a developer and a developing team a freedom to operate. So we said AWS as a paradigm exists. AWS provides you a service for networking. It provides you a service for databases. So you know exactly where you want to go to do a particular task, right? And we said, let's follow that paradigm. And let's say how do we develop a common set of reusable components that help us focus on data engineering, unstructured data ingestion, linking ontologies to your physical data, and start building out assets in that particular space. So what we'll do today as part of this presentation is actually walk you through and show you a demo of, let's say, if you had to build these out as reusable components, what would they actually physically look like? Yeah, so for us, right?
So the platform that we've developed is really organized around several categories of components and services. So the first are our data ingestion assets. These are focused on both traditional data engineering aspects that you need, extraction, transformation, data preprocessing, and intermediate storage, as well as the NLP framework for our unstructured text processing and knowledge mining. Of course, this is a platform for knowledge graph construction, so the core component are the knowledge graph utilities and ontology assets that power that. And we also realized that with any use case that involves a lot of unstructured data, typically benefits from some curation. So building in annotation, provenance, and lineage, and thinking about integration with annotation tools like Label Studio is a key part of the design. Lastly, as the last presenter also noted, knowledge graph is really only as useful as the interface is provided. So whether that's programmatic or visual. So we also have modules like Elasticsearch-based semantic search meant to enable downstream applications to consume from the graph and power some of their capabilities. All right, so we now have a brief demo that will walk you through and kind of show you some of those components.
Yeah, so in today's demo, we'll focus on the middle block, right, where we have our common components to enable data ingestion. And what we'll do is we'll go through a document or a research paper that somebody has published on PubMed and take you all the way through how you would have created in the knowledge graph, right, for a particular use case. The use case we are looking at today is medical insights. Like, let's say if people are interested in figuring out how and what other trials and research has been done in a particular biomarker space or a particular product space, how would you go about finding that information? So as Ashley mentioned, we have several components. Right? The first thing that we're interested in is a common data ingestion framework. So let's say if you take this particular article from PubMed where there are many things that are of interest to us, right? So you have a title so that you know exactly what people are looking into, what biomarkers are being looked at, as well as what is the disease area or a therapy area, right? So you've got, let's say, non-small cell lung cancer is a topic of interest in this particular paper. There are many authors, sometimes specific authors are interest to you, and you have an abstract and you have content here, right? So in this, the video has restarted, but in this space, right? So looking at this PubMed paper, you see, okay, I have a ton of information of interest. How do I structurally extract all the entities and relationships I'm interested in? And I also have figures, tables, and charts that are part of this particular diagram, right? So you need to be able to extract things like topics, authors, diagrams, tables, charts, and then start linking them to each other to derive insights. So the first thing that you take care of is a common ingestion framework. Each of these websites offer you a series of APIs, but you need to be able to scale them and structure them, right? So you need to develop a particular reusable asset which makes, let's say your problem statement is interested in NSCLC, right, non-small cell lung cancer. You should be able to configure and define that, bring me everything that is available from non-small cell lung cancer. So once you pull this information, what do you do, right? The first thing you do is break it up into sections, right? You start figuring out what sections of data is available and what exactly your paper contains, so that you can start mining your insights and so that you can start mining your entities. So the first thing you see that we have developed a series of adapters for our common data sets like PubMed or AACT, where you can start extracting things like abstracts, sections, and you start seeing things. If you notice this area where I'm highlighting is, let's say there was an image or a table, it would have created pointers to you to say that, okay, there are images, there are tables, there's more information around in the introduction around an author, there is disease areas, and it starts identifying and just simply says the first thing I'll do is sections, right? Why are we doing this? Because one of the first things an NLP engineer does is localization, right? So that you understand what section your components of interest are available in. So you take care of figuring out and tearing your document into various pieces, because eventually you want to get into entities like entities of interest. Entities of interest in this particular document for us were, we wanted to understand the age of the patient population, biomarkers that were being studied in this research paper, drugs, endpoints, ethnicity, because we are trying to look at medical insights, right? What type of trials are being run for in the medical space. So we figured each and every scientific organization has their own way of doing things. So how do you develop a framework where, let's say you're interested in specific entities like age, biomarker, you need to be able to use your own NLP model for each of these. And what this platform enables you is that, you see the picture on the left of the screen, is that a way to identify and define custom modules for every entity of interest. So let's say biomarkers, and GPT is good at identifying biomarkers, right? BioGPT. So you should be able to define that. Let's say I'm interested in biomarkers. Is there a dependency on any other entity of interest? If not, which section of the document to look into, and then for entity recognition, which particular algorithm to run. So you should be able to define, say, extract biomarkers using GPT, extract endpoints, extract age using a regex, extract ethnicity using a regular expression, extract location using a geolocations endpoint. Because in order to get the most accurate insights and the most accurate entities and relationships, you need to be able to give your end users flexibility and customizability, right? So this platform allows you to do that, so that for every document, you're continuously extracting the entities of interest using specific algorithms and keeping a track of where what came from, right? So we'll also show you after this how we keep a track of where which entity was created from and maintain provenance. So once we run this module which extracts various entities, what is the next thing that that we do, right? So the data scientist doesn't know scale, right? They don't know how to. We don't want to put the burden of figuring out containerizing their models for entity extraction. We figured we shouldn't put the burden of um, distributing models to the data scientist, right? We want our scientific users to focus on insights. So what this particular tool does that we advise people who are building a scalable AI solution is that develop your own way to containerize modules that are being developed by data scientists. So they should be able to plug in their NLP module into a containerization module that allows you to generate the right scale at the right time. So this runs, and this is the module which is taking care of the containerization, name entity recognition, takes care of creating the various components. Second thing that we execute here is standardization, right? Because everybody refers to the same things by different ways. So standardization module is a third component where you saw in the previous screen that you could configure a biomarker, you configured which algorithm it came from. In the third column on the screen, you also could configure what standardization methodology to use. Your organization might have one, so we tell our clients that use yours, or if there are many public taxonomies or ontologies, we allow you to stitch those as well. So now the same diagram or document that we saw from earlier, right? Oops. The same document that we saw from earlier now has a lot more information, if I can get to it, right? So this is the document we saw from earlier, right? Through the extraction module, you were able to extract things like biomarkers that have been enabled, like a power region and the entities. You also have a way to exactly tag from which location within the document the entity was extracted out and what is the type of entity that was extracted. So the same text document starts changing. Right now you start seeing that I have provenance, that which tells you what text something came from and what is the value of certain components that was extracted. All right, the last thing that we take care of is simply taking the entities of interest, taking the relationships that were extracted and then load it into our graph model. For this purpose of this demonstration, we have used Neptune as our graph, and you get a series of TTL files that most people are familiar with. Now, this is the output, right? You start seeing an unreadable graph and an unreadable mess of data that gets created. This is simply linking age, entities, biomarkers, drugs, diseases out of all PubMed documents from NSCLC. So this is a representation of us crawling through around 150,000 documents in the NSCLC space on PubMed. So this is unusable by end users. Users cannot make sense of this. So that's why even in the previous presentation, search was mentioned, right? And what we've done is, let's say you take a simple representation, right? You have two documents, you've got endpoints like progression-free survival, you've got biomarkers that have been represented. This provides you a nice simplified view of search. And the way search has been enabled in this use case was using a UI where we developed this is a UI example of a UI where that was developed on top of this particular knowledge graph. So let's say if you're interested in KRAS, right, which is a biomarker, the user can simply type in things like KRAS and you start seeing insights that are developed on the basis of research papers, things like graphs, which tells you that how many studies were executed with progression-free survival as an endpoint in the KRAS space, how many studies were executed as a stable disease toxicity. And if you see, nowhere in the search query did we tell them that KRAS is a biomarker. Right? We basically told them that simply using these terms and our knowledge graph, your search was able to map the fact that, yes, you entered a search term. I know through my knowledge graph that this search term is connected to the biomarker ontology, and then that's how you start developing insights on top of it. So we found out that any cases where we've released graphs as is have not gotten much use, but when you're starting to surface end users insights on top of these graphs, these accelerators help you in that particular space.
So we'll now just zoom in a little bit on the different components, just to briefly recap what you saw in the demo. So first, we have the data ingestion framework. this has several subcomponents, one being the data source connectors. So we have pre-built connectors for things like PubMed, for AACT for clinical trials data, but these can easily be extended, and you can plug in connectors for various sources as needs arise. Next, we have configurable processing steps. So these are pre-built configurable steps for things like conducting data quality checks, storing the raw data, parsing images, and storing those with pointers back to the original documents, as well as for pre-processing that data before it goes to the NLP pipeline. And all of this is orchestrated through our Airflow templates, so that we can easily scale and configure these pipelines. So next, we have really for any unstructured text use case, the Workhorse, which is the unstructured text processing framework. So as you saw, the first step is localization. So this sets the document context, breaks it up into different sections, and the sections can be configured. So if you want to focus on specific sections in order to use different models for those within the extraction part of the pipeline, or you want to have sections where you plan on weighting those differently, perhaps, and how you're going to pull that data into the graph. This is the step where you can configure that list of sections. So next, entity extraction. So as Jaipal mentioned, this is really, we've designed this so that our data scientists can bring their own models. They can easily integrate new models, say that given the explosion in the large language models lately, they can quickly create a new one, test it, and drop it into the pipeline so that it can be run with the same standard output. Then we have the standardization. So many of these extracted entities will need to be normalized either to something that's pre-existing in the graph, or to a standard source. Like for different medical indications, you might use MEDRA. And lastly, the relationship extraction. Again, our data scientists bring their own models that they've trained on their data for different types of relationships, and they can run this as part of the pipeline in order to extract those relationships between entities to create the graph out of as well. All of these are the main steps, but these are all meant to be run as part of a pipeline that also does dynamic batching and scaling so that we can parallelize this and be able to run for large amounts of data within reasonable timeframes. So, and lastly, we have our graph generation. The output of the NLP pipeline is standard formatted JSON. So we have utilities to convert that into RDF using configured ontologies. So typically for each use case, we'll have a domain-specific ontology, whether that's a public one that fits that use case or something that's been developed custom internally. The graph archival step will allow us to archive previous versions so that we can maintain consistency in the graph, and then we load that data. Our default is Amazon Neptune, but we've done this with Autotext GraphDB as well. And in parallel, we have the option of pushing the RDF data also to Elasticsearch to enable the semantic search for our downstream applications as needed. We also maintain versioning information. So we have an internal versioning table. We update using the run metadata for each newly inserted entity or relationship or updated resources so that we can maintain version info and lineage throughout the graph. And lastly, as part of the graph and ontology assets, we found that most of our use cases that involve like scientific literature or other documents, the structure and the context of the document is important. Your graph ultimately might be focused around the extracted knowledge and the domain-specific classes and relationships, but you also oftentimes want to be able to go back to that document to be able to look at articles that have been published by the same author or articles in certain publications. And so we want to represent that, and that's not necessarily very specific to a particular use case. That's common across many. So we use we've extended the SPAR document components ontology to be able to represent the documents, the document metadata, the different components, and the annotations so that we can link what's being extracted from the documents to the ultimate instances in the graph. Okay. And So lastly, to just wrap up, really we found that for us, this is enabling our internal use cases to be able to move much faster to implement knowledge graph solutions for different healthcare and life sciences use cases. And it allows our data scientists and engineers to focus more on the knowledge extraction side than the data engineering and graph construction. So this is enabling much faster turnaround time and giving us a lot more standardization and the ability to scale and build on top of something rather than building something from scratch every time. Any last words?
Yeah, thank you. Usually this is an hour-long demo. This is the first time we've done it this quick.
Hello. Great talk. Thank you. Way back early in your talk, you were talking about the ingest of a particular PubMed article, and I was wondering, you talked about the title, the abstract, but you didn't really mention some of the other more specific metadata. I'm thinking mesh and some of those other vocabularies. I was curious if that is also ingested, and if not, why?
Yeah,
Why
so
not?
we do ingest that. So there's part of it is we're using that metadata like mesh subject headers oftentimes when we connect to PubMed in order to filter the information we bring in. We might look at, okay, we're going to bring in for this set of subject headings. So that's brought in. And then we do link it. So in the document model, we are capturing some of that metadata as well from the original source.
Thank you. That's excellent work, and you've built some really interesting, frameworks here. But I can't help, coming from the NIH, I can't help but wonder if what this will generate is a lot more graphs that are still completely incompatible with each other. And I'm often looking for ways that we can try to, make it available for people to create graphs that will be able to be connected and made publicly available. Obviously, that's not everyone's plans. But I'm wondering if, you've thought about, it sounded like you need to have your clients bring their own NLP and plan their, for their own ontology that they want to, use for the final graph. Have you thought about trying to at least offer a more general, something to your clients to say you could bring your own, or we can use this high level ontological framework that will be compatible with a lot of your fellow fellow clients, that then you could potentially work together and connect your graphs together, for example.
Yeah, so there for our clients, we always push them more towards public ontologies versus bringing their own built ontologies, right? So what we are essentially trying to figure out is, again, from members of the Pisto Alliance, right? So FHIR formats, there are formats around, there's also safety formats, right? So there are a lot of public ontologies that we try to focus the solutions around and build our adapters around. Because without public ontologies, these graphs will not be able to connect to each other, and then and if you don't contribute back to these public ontologies, then the world will no longer, it won't be a true connected data vision, right? So our thought is even if with you coming from the NIH also has a lot of good ontologies and taxonomies that they've published. So we strongly reference those. What we're trying to tell folks is that you use high quality or well-defined semantic frameworks that what we'll bring to you, or what your IT team should focus on is developing scale around it. Right? So our goal is we'll give you scale, but please follow the public ontologies as much as possible, and respect what your data scientists are doing, because they also know how to extract the right values for the right entities. So that's kind of the whole premise.
Yeah, I think to your point, this needs to be coupled with a set of best practices and standards and a knowledge of the available ontologies and how to extend them and leverage them in order to make sure that you can connect that data and it is truly interoperable. Yes.
Any other questions? Complaints? All right, complaints, go for it.
This is really cool work. I really enjoyed your presentation and just the entire work that you've done. I'm from the NovaGraph project, and one piece in our graph that's really critical for humanitarian aid agencies that we partner with is for them to identify experts in our graph. And these experts are primarily in the medical domain, but they also want to find experts who are in the medical domain but have interacted specifically with interacted with certain disaster situations, so they can reach out to them in the ground when a disaster happens. And in addition to that, they also want to see information about where that person is located, and also like do they have experience working with, for example, diabetes specific to hurricanes, but hurricanes that happen in this particular region. So those are the kind of use cases that use case scenarios for that they are looking for, and that's how we model experts in our graph. So very spatiotemporally focused. Like there could be experts. Some of the experts that we primarily extract are experts from semantic scholar publications, and what we've seen is a person who has a lot of publications related to a specific topic no longer is pursuing that work anymore. It's like they're not an expert anymore. So that brings the temporal component into picture, right? So our graph right now has experts that we've extracted from semantic scholar, but slowly what our stakeholders are saying is this is cool, but honestly we want to see people who've more practically like done or like administered aid in a particular scenario, who most likely have not published scientific articles, right? So have you kind of like tried looking at different sources for your experts besides just PubMed articles? Like, are there other unstructured sources that you've tried to scrape your expertise information from? And if so, can you use the same methodology?
Yeah, so I'll answer the question in two parts, right? The first one is temporal aspect, right? So one of the main reasons we started maintaining our document provenance ontology is that it gives you a time it was published and when the publication was commissioned, right? So that takes care of the time component when you start filtering out entities or relationships of interest by simply filtering out the document that it came from. The second one is pulling out experts, right? So we have looked the same framework we have also utilized on Word documents, because Word documents also have sections, also have areas. We've also pulled out information from PowerPoints for one of our clients where we looked at extracting entities using the same processing framework for PowerPoint creators and PowerPoint authors, right? So this is just a generic framework. You can use it on various components. The reason we highlighted PubMed and was to simply tell you that you need to have your data ingestion sorted, right? You need to figure out what and some public companies do offer a lot of pre-existing APIs, and this is simply a reuse of PubMed's public API. It's not something that we created to scrape and extract documents. The same type of reusable components Windows also offers for Words, for PowerPoint. You reuse those. You plug it into our containerization modules, which takes care of parallel execution.
Thank you.